My name is Mitchell Ford. I'm a PhD student at Oklahoma State University. And for my talk at the 2021 Oklahoma AIAA ASME Symposium, I'll be discussing metachronal, synchronous, and hybrid kinematics in aquatic paddling. My co-authors are Erica DeLuca, an undergrad in our lab, and Arvind Santanakrishnan, who's the PI for the lab. Remotely operated and autonomous underwater vehicles are important in oceanographic, military, and scientific endeavors. And one of the major problems that they face is that they're bulky, they're not very maneuverable, and they're expensive to operate. There's been a push to use bio-inspired underwater vehicle designs to try and address these issues, with two examples here on the bottom of the screen being the TunaBot, which is a tuna-inspired robot from the University of Virginia, and a jellyfish-inspired robot from the Max Planck Institute. Each type of bio-inspired design will have its advantages and its disadvantages. And one design that hasn't really been explored as much is a paddling propulsion system, which uses multiple legs to generate thrust forces. And advantages to that type of model are that you don't require sophisticated materials like for a soft robot. They're fault tolerant because if you're using multiple appendages for propulsion, then if one propulsor fails, you'll have others to fall back on, and they're highly maneuverable. And so we wanted to look at using metachronal paddling as a propulsion system. And so what is metachronal paddling? It's a propulsion strategy that's commonly used by a huge number of crustacean species, in which they have multiple pairs of abdominal limbs, legs on their abdomen, which they stroke in sequence, starting from the tail most paddle, you can see on the right of the video here, and going to the headmost paddle. And so you can see that there's a highly coordinated motion here, but the paddles are not moving in a synchronous fashion. There's a delay between the motion of each appendage. And so the power stroke is then there where the leg is moving from pointing more directed towards the head to towards the tail, and that generates your forward thrust. And then there's a recovery stroke to get your leg back into that starting position. And with the phase delay, the metachronal wave, which is the delayed motion here, moves from the tail to the head, which is the same direction as the swimming motion. But not all crustaceans use a purely metachronal stroke. There's burst swimmers such as copepods and mantis shrimp, which aren't actually shrimp. This is a mantis shrimp in the video here, are known for their rapid acceleration. And they use kind of a hybrid stroke where there's a metachronal power stroke, but there's a pause at the end of the power stroke to wait for the other limbs to finish. And then all limbs recover it in a synchronous or nearly synchronous fashion. And these organisms, they can almost instantaneously accelerate to hundreds of body lengths per second swimming speeds. And they use this to capture prey or escape predation themselves. And so we wanted to look at what makes this hybrid stroke so good for rapid maneuvering. So we designed a robotic model, which we placed on an air bearing. You can see on the left here. We used 5 different solid acrylic paddles, each paddle driven by its own stepper motor. And we prescribed a series of metachronal on the top plot in the middle here, and hybrid, which is the bottom plot here, kinematics with varying phase lag, which is phi, is defined on the top, and varying stroke amplitude, which is theta, defined on the bottom here. The different test conditions that we used are shown on the right, with the circles representing metachronal stroking, while the squares represent the hybrid stroke. The dark gray zone here at the top is conditions that are not achievable using a purely metachronal stroke because it would cause the paddles to collide with each other. And so we had a idea that perhaps getting into this zone here where you have a large phase lag, but also a very large stroke amplitude could in some way benefit your maneuvering performance. So using particle image velocimetry, we were able to visualize and quantify the metachronal swimming wake. We found that there's not too much difference, particularly in the velocity in the wake between the metachronal and the hybrid kinematics when using the same stroke amplitude. That'll be the left is metachronal kinematics and the center is the hybrid. However, there was a little bit more downward direction, it seems, using the metachronal wake, while the hybrid wake is really directed mostly just to the horizontal direction. And then you can see that there's a large increase in velocity when using a larger stroke amplitude on the right here. And so we calculated the vertical and horizontal momentum flux from these PIV data sets in order to actually quantify how much stronger the wake was in one direction or another, and with changing stroke amplitude. And so we found that for both metachronal and hybrid strokes, your horizontal and vertical momentum flux both tend to increase as you increase the stroke amplitude, no surprise there. But that there actually wasn't really any statistically significant difference between the metachronal and the hybrid stroke in the horizontal flux. We found that the vertical momentum flux, there is a slight difference. We do get more vertical flow from the metachronal stroke as compared to the hybrid stroke, but that the strongest predictor of the momentum flux in both directions was actually the stroke amplitude. And that's what you're able to increase by using this hybrid stroke. We also tracked the movement of the robot as it swam along that air bearing. We've got the position for 3 different conditions shown here: metachronal with 15% phase lag, hybrid with 15% phase lag during the power stroke synchronous recovery, and then hybrid with the larger stroke amplitude, 115 degrees instead of 75. The top plots here are the position of the model, while the bottom shows the velocity. And we found that there's not too much difference in the amount of time that it took the metachronal and the metasync with the same, the metachronal and the hybrid kinematics with the same amplitude. As just the hybrid finished slightly faster their travel, but the larger stroke amplitude finished much faster than both of the lower stroke amplitude. Again, on the bottom, we see the velocity for each model, and we see that each accelerates with a decreasing slope. We don't get to a final steady velocity, but we did find the final velocity at the end of the travel, and we found the peak acceleration for each condition. We found that the velocity at the end of the travel actually does start to level off as you increase above 75, 95 degrees. There's a much smaller difference between the final velocity at 95 degrees than there is at 115 degrees. There's not as much change there. However, the acceleration as we increase the stroke amplitude does continue to increase, with the acceleration being very important for that maneuverability quantity. If you can't accelerate quickly, then you can't escape predation and you can't maneuver as well, which is what our goal is with the AUVs. So in summary, we found that hybrid kinematics result in a slightly slower speed when compared to metachronal kinematics for constant stroke amplitude, just very slightly. We found that the metachronal power stroke and synchronous recovery stroke, those hybrid kinematics, They allow paddling organisms and robots to increase the stroke amplitude. And we found that as stroke amplitude increases, that's the strongest, that has the strongest effect on the swimming speed and acceleration by increasing both. These are my co-authors here, Erica DeLuca and Arvind Santanakrishnan. And I'll be happy to meet everyone at the symposium. My email's on the bottom of the slide if you have any questions. Thank you.